Okay, so we have an experimental type problem here. We're given sort of a setup that's kind of pre-made and listing of equipment, and we have to show how we're going to use that equipment to accomplish a specific goal. And that goal is to measure the speed of sound in air. So a lot of this equipment is equipment that we haven't used or seen in the lab. So the first thing to do is really identify what each thing does from sort of the text and the description. So the first thing that's kind of unusual is the sine wave generator. Basically, that's just something that makes a sound wave. But because it's a wave generator, you can set it, it says adjustable frequency. So you can pick whatever frequency of wave that you want for it to produce. So you could have a 200 hertz sound wave or a 400 hertz sound wave or anything in between or so on. The second is this waveform display. And basically a waveform display is, as it's pictured, all it does is it shows the history of the amplitude of the wave at the point where the microphone is located, right? So basically it makes a history graph for you. So that waveform display shows us the amplitude as a function of time. So we can like measure frequencies and periods using that, and also amplitudes, right? Okay. So we see from this setup that we have a tube of a certain length, one end open and the other end closed. And that should immediately make you think, oh, a standing wave, right? We've done standing wave stuff with an open closed tube where we had nodes at this end and antinodes at the other, right? And if that is the case, right, our standing wave will look something like this, where this whole thing is length L, and the red bit is, not L, is 1/4 of a wavelength. Or we could do it where it's 3/4 of a wavelength, right? That would also satisfy those node and antinode rules, or 5/4 of a wavelength, and so on, right? So there's a relationship between L and the wavelength because we have a standing wave. So what we want to do is describe how we're going to adjust L, keeping the frequency constant, or how we're going to adjust the frequency on the sine wave generator, keeping L constant, to produce a standing wave. Right? That's the idea. Right? So I'm not going to write down the procedure step by step, but the idea is that we'll set the sine wave generator up. We'll pick a frequency, whatever it might be, and we'll turn the thing on. And then we'll look at the waveform display, and we'll see if it looks like it's a maximum amplitude. That would be a standing wave. If not, we'll adjust either the movable piston, which changes L, or the frequency that we set on the sine wave generator, which changes the wavelength, until we get that maximum interference, right? So if we get it sort of wrong, the waveform display is going to look actually, I'll not even label that. This is like so the waveform display, when it looks wrong, will look kind of like this, right? You'll hear it, but it won't be a lot of interference that makes it louder. When it's right, it'll be like this blue line, right? Big amplitude. So when it looks like that, then that's the sign that we've made a standing wave. And when we've made a standing wave, we know that there's a relationship between L and these wavelengths. Namely, that 4L over N equals the wavelength, right? And so once we make a standing wave, we know that condition is true. So we can calculate the wavelength, right? And we know the frequency. That's what we set on our sine wave generator. So then we can use V equals lambda times F to calculate the speed of sound. And this is set on generator, right? And so that's basically it, right? Again, there's two options. We can either fix the frequency and change the L by moving that movable piston until we get a standing wave, or we can fix the movable piston in place and adjust the frequency on the generator until we get a standing wave. Once we get a standing wave, we can calculate the wavelength using that relationship, using the meter stick to measure L. Ideally, we want to describe what n should be, right? We should set it up sort of like, we start at the lowest possible frequency and slowly increase. That way, n would equal 1 if we start at that lowest frequency. Otherwise, we wouldn't necessarily know what it is. And so on. And then once we know lambda, we use v equals lambda f to calculate the speed. Right? And that answers both parts A and B. They kind of go together. Basically, if you were doing this question, the way to do it is to go through the procedure, and as you go, right, pay attention to the calculations you have to make in that procedure, and then demonstrate sort of the calculations separately in part B. So like you would say, well, we need to record the length capital L, and then from that, calculate the wavelength lambda. And then part B will say, how do we calculate the wavelength lambda using the length capital L? Well, that's the formula right here, right? And then you actually show the actual calculations. That's part A and B. Part C is a bit of sort of experimental quality stuff. So if we find one standing wave, that's good. We have one measurement for the speed of sound. But it'd be a lot better if we could have multiple measurements, multiple sort of standing waves that fit, and measure the speed of sound from all of them, and then calculate some sort of average, right? Or a graph. Okay? So if we have the formula v equals f times lambda, this kind of gets back to what I was talking about before. We find one standing wave. We can then adjust either one of these variables. So if we picked a frequency and moved L around and found a standing wave, then to get better data, we could change to a new fixed frequency. So we could do trials at, say, 100 hertz, then 200 hertz, and then adjust L to find V, and so on. Or we could do the opposite way around. We could pick a length. Let's say we're going to do, we're going to do 1 meter, and then we adjust F to find V. And then now we're going to pick a new length L, which means we picked a new wavelength, and so on. So the idea is you have to pick either one of these two to say we're going to pick different values for that. Right? And then we want something graphed. So this function, if we make one of these are independent and the other one are dependent, right? In this case down here, the frequency is independent, and the length, I guess I'll go with wavelength, is dependent. Right? We control the frequency of the sine wave generator, and then we adjust the length L, or the wavelength of the wave, to match it to get a standing wave. So if this is the case, right, our graph should look something like this. There has to be something with frequency on the x-axis, and our y value has to be related to lambda. So if I take this equation and rearrange it, we're going to get 1 over lambda equals 1 over v times f. And if this is that y equals mx format, right, y equals m, and then x, right? So this tells us that our independent variable, the frequency, is on the x-axis. That's correct. This tells us that our y variable can't just be lambda. It has to be 1 over lambda, right? That's what goes there. And we'll get something that is linear, but the slope is 1 over v. And so we can use the slope of the graph to calculate the velocity. There are other options, right? If we did the other trial, we'd be changing which was our independent and dependent variables. We'd get something like 1 over f equals 1 over v times lambda. And so our graph would look slightly different, but the slope is the same, right? That would work. The other option is we could flip everything, right? We could do lambda equals v over f, and so then we'd be plotting 1 over f and lambda, and the slope would then be v, right? Any of those are possible options. The key is it starts with this formula, and based on what you are varying, you have to identify the independent variable, your x-axis, and then rearrange so that way you get a dependent variable for your y-axis, and then a slope as well.